Okay, hi everybody. Welcome to VSPG. Today we have a talk by Professor Ronny Schoenberg titled The Mode and Timing of the Oxidation of Early Earth's Atmosphere-Geosphere-Hydrosphere System. Next week we have Professor Andreas Kapler, also from University of Tuebingen in Germany, and this talk is titled Geomicrobiological Processes and Banded Iron Formation, Deposits, Banding, and Diagenesis. So Andre is going to introduce Ronny for us today. So go ahead, Andre.
Yeah, it's a pleasure to introduce Ronny Schoenberg. Ronny is originally from Switzerland and did his training in University of Bern for undergraduate and graduate degree. And for graduate degree, he worked with Jan Kramers on, I guess, on Limpopo belt, but on development of rhenium osmium isotope systematic and application to ore forming process and crust mantle evolution. He followed with research fellow and research assistant and senior research assistant appointments in the University of Queensland, in Brisbane, in Australia, in University of Hanover, in Germany, and then in the University of Bergen, Norway. And in 2010, he took position of professor of isotope geochemistry in University of Tuebingen, where he is based now, and his research interests range from redox evolution of surface environments, application of radiogenic stable and non-traditional isotopes to magmatic ore deposits, to igneous process, and to modern oceanography. And he published on a number of non-traditional isotopic systems, including chromium, iron, zinc, and many other elements. So with this, I pass it to Ronny.
Thank you very much for the introduction, Andre, and also thank you for giving me the possibility to present results from our research projects concerning the oxidation of earlier surface environments in this virtual seminar. I'd like to start with this very famous illustration or graph by Tim Lyons from 2014, and some of us might get tired to see it because it's in so many talks and presentations, but it's still a very good illustration of how atmospheric oxygen evolved through Earth's history with extremely low values, lower than 10 to the minus 5 present atmospheric levels, to about 1%, 3% maybe, in a first big step at the Great Oxidation Event 2.4 billion years ago, and then in a second major step to approximately present-day levels of oxygen in the Neoproterozoic oxidation event later on. This talk here will concentrate on the Great Oxidation Event, and I will give you a broad, very, very broad overview about the progress of understanding and also quantifying the evolution of atmospheric oxygen levels from the Archean towards the GOE, so about this time window here. And thereby I will highlight some of our own projects on which we worked at the University of Tübingen, mainly in collaboration with Nick Bucas, who very unfortunately passed away early this year. I will also present the results of a study on which we worked with Nick and which he was extremely fond of, which was very dear to him, essentially until he was admitted to the hospital some 3 weeks before his passing. From geological observations from the geological record, we know for long that around 2.5 to 2 billion years ago, the redox conditions in Earth's surface environments changed from reducing to slightly oxidizing conditions. And in particular, these observations include the oxidation of iron 2 to iron 3+ in paleosols, the disappearance of detrital, uraninite, and pyrite, and the appearance of red beds in continental sediments, and that's due to the oxidation of uranium and iron, and the appearance of manganese oxide deposits, as well as marine sulfides and phosphorites. So we do know just from sedimentological, mineralogical observations that around this time frame here, there was a significant change in the redox of Earth's surface, and also affecting, of course, the climate of Earth's surface. The many studies of Dick Holland and co-workers on paleosols, and here highlighted the work or the publication by Rye and Holland from 1998, were the first studies to actually quantify this change in atmospheric oxygen levels during this time interval here, somewhere between 2.5 and 2 billion years. These investigations used the redox behavior of iron in paleosols, where iron 2 is released from minerals during pedogenesis and becomes soluble, and then is transported away from the weathering profiles by meteoric waters under anoxic atmospheric conditions, resulting in an overall iron loss. And we can see this here on this right graph. For weathering profiles that are older than 2.2 billion years, there's a significant iron loss. Or it becomes oxidized to insoluble iron-3 oxyhydroxides under slightly oxidizing atmospheric conditions, resulting in a retention, overall retention of iron in weathering profiles. The retention of iron during weathering depends on the relative rates of supply and demand of oxidants and weathering acids, which in the Archean is generally directly related to the ratio of partial pressures of atmospheric oxygen and CO2. Estimates of this ratio and the compositional change observed in weathering profiles allowed Rye and Holland in this publication here to calculate that atmospheric oxygen levels before around 2.4 billion years ago were smaller than 5 times 10 to the minus 4 atmospheres, whereas there was a significant change between around 2.2 to 2 billion years from about 2 per mil to approximately 3% or larger of modern atmospheric levels at that time. So this is really the first quantification of an oxygen level increase in the atmosphere. Mass-independent fractionation of sulfur isotopes, MIF-S, or sometimes also denoted S-MIF, is an extremely powerful tool to investigate early Earth's atmospheric oxygenation. And in the abstract to this talk, I called the disappearance of mass-independent fractionation of sulfur isotopes a game changer for our research community. And I quickly want to explain why I think this is a game changer. So, under anoxic atmospheric conditions, oxygen-free atmospheric conditions, UV dissociation of volcanic sulfur dioxide leads to the formation of sulfate and elemental sulfur, and this UV dissociation will create a mass-independent fractionation of sulfur isotopes denoted as capital delta 33S with positive or negative values if oxygen levels in the atmosphere are extremely low, essentially lower than 10 to the minus 5 of the present atmospheric level. If oxygen levels in the atmosphere build up, this dissociation will not work anymore, and thus all sulfur that we will find on Earth's surface in sediment, stored in sediment, will not show this mass independent fractionation anymore. So delta 33 sulfur values will be 0, such that we only then have mass dependent fractionation, MDF, of sulfur isotopes. This is an extremely sensitive tool for tracing atmospheric oxygen levels. And these here are graphs that show the results of James Farhar and colleagues' work on MIF sulfur, on the disappearance of mass-independent fractionation of sulfur isotopes at around 2.4 billion years. Here's the original work from 2000, and later in 2007, Farhar and colleagues published yet another paper with more data, and one can clearly see here highly fractionated sulfur 33S values, and after 2.4 there's a complete disappearance of this signal. Values will only be 0. That means we have a switch in atmospheric oxygen contents above this 10 to the minus 5 threshold. In 2007, Anbar and colleagues published another, what I may call a hallmark paper about oxygenation of the atmosphere. So from the 2.5 billion year Mount Grey shale in northwestern Australia, these authors reported enrichment of the redox sensitive elements molybdenum and rhenium, and also uranium, not shown in this graph, in these shales. And the idea here is that oxidative weathering leads to oxidation of these elements. And when they are oxidized, these elements become soluble. They can be transported from the continents to the oceans through rivers, and then they will be usually reductively deposited in marine sediments, and thus lead to enrichments in these sediments. And I really find this title still very good, a whiff of oxygen at 2.5 billion years. One can not only use the concentrations of these redox sensitive elements to say something about oxygen levels in the atmosphere. One can also use stable isotope variations. Here the example of molybdenum as the delta 9895 molybdenum signal. So the idea here is when these redox sensitive elements go through redox cycling, when they are oxidized, they become soluble, and then in the marine environment, these elements can fractionate their isotopes either through adsorption processes or through cycling from reduced to oxidized to reduced again. So as soon as one finds fractionated isotopic values in these elements that are away from the continental weathering background, then it is very likely that this element went through redox cycling and indicates at least some oxygen levels in the atmosphere. And here I highlight the work of the group from the University of Bern, mainly under the supervision of Thomas Nagler. That's work on the 2.6 to about 2.5 billion year old Campbell-Around carbonate platform in the Griqualand West area in South Africa. And we can see here some fractionated values of carbonates and black shales, and they seem to fluctuate. And these authors propose that these fluctuations of these molybdenum isotope values actually might be due to fluctuations in atmospheric oxygen levels. So through discussions with Nick Bucas, we came to the idea that it actually might be very interesting to compare these molybdenum isotope results from the Campbell-Around area of the Transvaal supergroup, but that's on the slope facies of the Campbell-Round supergroup with a drill core that is drilled down in, or that samples the platform facies of the Transvaal supergroup in the Malmani area. So in 2010 and then later 2012, we went from Tuebingen to South Africa to work with Nick Bucas and sample a drill core KMF5 that was taken in the Carltonville area, some 100 to 150 kilometers southwest of Johannesburg, and that really goes through the platform facies of the Transvaal supergroup. And here we can see myself, Nick Bucas, and some students from Tuebingen sampling this core, and Nick Bucas take a lot of time to explain to my former PhD students, Sumeya Erolu and Florian Kurzweil, what he can read from this drill core. And he was explaining very enthusiastically the Archean, Neoarchean world that he can see from such a drill core. So at the meantime, while he was explaining this, others, and that's me here, were doing the hard work and laying out more than 1,500 meters of drill core boxes. So here directly the results from this study. So this is the log of this KMF5 drill core here. These are the molybdenum concentrations. And here we see our molybdenum isotope results, all published in Erolu et al. 2015 and Precambrian research. And just like the Bern group, we also find these fluctuating values throughout the Malmani carbonate platform here. Now, Sumeya Erolu also investigated a single hand specimen of only about 15 centimeters length. And she micro-drilled this sample at different spots, measured the molybdenum isotopic composition, and found unfractionated and fractionated values in the overall order of the fractionation that we found in the entire core. And that made us think that maybe these fluctuations that we see in the core are not only due to actual fluctuations in the oxygen level, but might to at least some extent be due to sample bias. These small scale fluctuations we proposed were maybe due to redox changes within very localized redox changes within the microbial mats that actually form these carbonates. So all these information and many more information from, there's really almost hundreds of papers that appeared in the last 20 years about the oxygenation of the atmosphere towards the Great Oxidation Event. Ostrander et al. Devised or summarized all this information in this very nice graph here. And here you can see the MIF-S boundary of oxygen levels on the y-axis. And you can already see some fluctuations here, but an overall increase of oxygen levels towards the GOE at around 2.4 billion years here. But there's really significant fluctuations. For example, here, Anbar's whiff of oxygen. Before then, finally, the atmosphere becomes oxidized. So we go over this threshold value of MIF-S. In the project of my former PhD student, Lucille Rouet, we then thought it might be very interesting to also have a look at redox changes in the marine real, comparing shallow water to deep water environments. And we did that, or Lucille did that, on several drill cores of the Archean Biosphere drilling project in the Hammersley Basin in northwest Australia. Lucille worked with other fancy isotope systems here. So apart from molybdenum isotopes, she also used tungsten isotopes and chromium isotopes. And here you can see the age of the different drill cores that she samples and the results. And again, these redox sensitive elements, when you see fractionated values away from that igneous inventory or continental crustal values, then you most likely go through redox cycling due to oxidation reduction cycles of these elements. Each of these elements has different redox potentials that switch them from reduced to oxidized state. So tungsten is very easy because the level here is at the lower waterline. Essentially, this means tungsten in all Earth surface environments will always be oxidized. Molybdenum, on the other hand, has a threshold value at a pH 7 of about -0.25 volts, which means you need a redox potential of that level to get molybdenum 4 oxidized to molybdenum 6, and chromium is even much higher. There, this threshold value is plus 0.42 volts, which is essentially the oxidation EH or the EH of the modern ocean. So we can see no fractionated chromium. We see unfractionated molybdenum isotopes until about 2.5 billion years ago, and we always see fractionated tungsten isotopes. And from this, Lucille could devise a model of shallow and deep ocean redox behavior. So from 3.5 to about 3 billion years, we only see tungsten cycling throughout the ocean, and that means that the redox potential of shallow and deep oceans must have been between the threshold value of -0.4 volt for tungsten, but still below the value for molybdenum oxidation of -0.25 per mil. Between 3 billion years and 2.7 billion years, we then start to see some fractionated molybdenum isotopes in shallow water environments. These are data from Marie Toby and co-workers published in 2019, where they find fractionated molybdenum isotope values in carbonates. But at that time, there's still no fractionated values throughout deep water successions in black shales, for example. Between 2.7 and 2.4 billion years, we then do see fractionated molybdenum isotopes also in deep water environments, which shows us that also in these environments, the redox potential must have been gone now over the threshold value of molybdenum of -0.25 per mil. And post 2.4 billion years in our data set, we can still see molybdenum cycling, which means in shallow and deep water, we are above the threshold value for molybdenum, but we don't see tungsten isotopic variations anymore. And this is because tungsten now is not being deposited anymore in these deep environments, because potentially they become more enriched in sulfidic, in sulfides, so they change from ferruginous to sulfidic, and under these conditions, tungsten simply stays extremely soluble and is not being deposited into sediments. So when we go back to this nice graph of Ostrander with the atmospheric oxygen evolution, we can now overprint our marine EH evolution. I added a second axis here, giving the redox potential, oceanic redox potential, with the threshold for tungsten, molybdenum, and chromium. And we can see that from around 3 billion years ago, we clearly go over the threshold value for molybdenum in the surface ocean, but not yet in the deep ferruginous ocean. And then at around 2.4 billion years, we potentially change the deep ocean from a ferruginous to a sulfidic environment because above the molybdenum threshold value. But we don't see tungsten cycling anymore because it's simply not deposited into these sediments so strong that it overwhelms the detrital background. Okay, I want to draw your attention to a wiggle in this atmospheric evolution of Ostrander and colleagues here, lined out in red here. So there's a strong fluctuation or oscillation in atmospheric oxygen levels, starting with mass-independent fractionation of sulfur isotopes, to mass-dependent fractionation of sulfur isotopes, back to mass-independent fractionation, and back again to mass-dependent fractionation of sulfur isotopes. So the increase of atmospheric oxygen does not seem to be somehow linear, but it's extremely oscillating. And this particular wiggle here is due to a dilemma that we have in the geological record, or how we interpret the geological record, in particular in the relationship between the Deutschland Formation and the Ruihochte Formation of the Transvaal supergroup in South Africa. So in early reports from the South African Committee for Stratigraphy in 1980, these two formations were reported to be independent units, deposited at different times with a time gap even of some 80 million years between them. And that comes from the observation that the Ruihochte Formation conformably underlies the Time Ball Hill Formation, whereas at the top of the Deutschland Formation, we always find an unconformity, and this Deutschland Formation can also directly underlie the Time Ball Hill Formation. Later work then, for example, by Kutzi et al. And others, correlated the Time Ball, the Deutschland, and the Ruihochte formations, and interpreted the formation of these formations to be contemporaneous. Essentially, they are one and the same formation that just were deposited in slightly different environments at different distances from the paleoshore of the Transvaal Basin. So why is this so important? How we treat these two formations? In 2009, Gu et al. Published sulfur isotope data from the Deutschland Formation here, where they found a switch from mass-independent fractionation of sulfur to mass-dependent fractionation of sulfur in the Deutschland Formation. And they interpreted this to be the exact location or timing of the Great Oxidation Event, where the atmosphere went from anoxic to slightly oxidizing. In 2016, Luo et al. Then published sulfur isotope data from the Ruihochte Formation, and they also found this switch from mass-independent fractionation to mass-dependent fractionation of sulfur isotopes. They also placed the GOE here very close to the onset of the Time Ball Hill Formation. So Luo et al. Correlated these two drill cores, or correlated these two formations, the Deutschland and the Ruihochte, and proposed that there is a single oxidation event at the Great Oxidation Event stored in these two formations. Here in this graph, you can actually see where the Deutschland and the Ruihochte Formation can be found. So just in this area here of the Kapval Craton or of the Transvaal Basin, the formation that is underlying the Time Ball Hill Formation is called the Deutschland Formation, whereas everywhere else in the Transvaal Basin, the formation that directly underlies and conformably underlies the Timeball Hill Formation is called the Rooihoogte Formation. However, there are still other groups that define these two formations as being independent from each other, not contemporaneously deposited. For example, here, the very good dating work and very important work of Gamsley et al., who redated the Angeluk lava and thus put the package of the Hatta-cell formation, the first appearance of manganese oxides in the Transvaal supergroup back by 200 million years. But these authors, they treated the Deutschland and Rooihoogte formation as two independent formations, each of which having this switch from mass-independent to mass-dependent fractionation. And as such, they proposed an oscillation of oxygen increase throughout the timing of the deposition of these formations here. And this was a problem that was very important for Nick Beukes, and I had many discussions with him around this problem. Are these now the same, or are these contemporaneous formations or not? And finally, in 2016, Nick Beukes and colleagues got funding from the Aguron Institute to drill several drill cores through successions of the Timeball Hill and Deutschland formation in this region here, and through the Timeball Hill Rooihoogte formation in this area and this area here. So in total, these are 4 drill cores, and the idea is to work on this drill core material sedimentologically and of course also geochemically, maybe also using geochronology to investigate, are these actually 2 different formations or not. So we were involved in this project through the PhD thesis of Julius, or we still are, through the PhD thesis of Julius Hafstein. And of course, we worked on the geochemistry and isotope geochemistry on these drill cores. Now I want to present some of the results that we came upon and then go into what these results could actually mean. So here we see the major element composition of these 4 drill cores, maybe quickly explained here in this legend. So 3 of the drill cores are from the Rooihoogte formation, and 1 drill core is from the succession Timeball Hill into the Deutschland formation. And that drill core, the symbols here are the red squares, whereas the other symbols are the Rooihoogte formation. And what we can see is that the elemental composition of all these drill cores and as such of the Rooihoogte and Deutschland formations are extremely similar, maybe with the exception of slightly higher manganese oxide concentrations in the Deutschland formation compared to the Rooihoogte formation, maybe at the upper end of iron contents and maybe at the lower end of silica contents, but they're extremely similar, which means the material from which, the detrital material from which these formations were formed is very similar. Earlier work proposed that most of this material of felsic to mafic composition came from the northeast of the Transvaal Basin, but there is also there are also papers that mention that a more mafic enclave also deposited some material into the Transvaal Basin from the northeast. And this here could actually explain why in this part here of the Transvaal Basin, where we have the Deutschland formation, we see a little bit more of the mafic components magnesium, iron at lower silica contents. There's also a significant foreland throw in the Transvaal Basin here, where the Deutschland Formation was deposited. So this here is close to the paleo shoreline. The paleo shoreline will be up here somewhere during the time of the formation of this basin. And we can see a deep foreland throw, then a foreland bulge, and then I wouldn't say a shallow ocean, but a large, let's say, platform ocean. When we look at trace elements, and in particular here, the rare earth element of the 4 drill cores normalized against the post-Archean Australian shale, we can see that these are very flat pattern. They're typical shales. They're not enriched. There's no clear seawater signal, maybe some indications here. But you can see that, of course, as black shales, these sediments are very much detrital dominated. There's not much difference here. Again, the Deutschland and the Ruihochte have very similar, not unexpectedly, very similar rare earth element pattern. We can also use different parameters. For instance, we can use chemical index of alteration or the index of compositional variability in these drill cores. And we can also see here that they are extremely similar in their elemental composition and in their CIA values, for instance. So all that material that has been deposited in these 2 formations is extremely similar. Now, this is a very complicated graph, and I might have to elaborate a little bit. I'll try to break it down to simple information for you. So here in the large graph A, we have our own neodymium isotope values or information here given as epsilon neodymium values. So the isotopic ratios normalized to the Core values, and we see the evolution of the neodymium isotopes here through time. And when we look at approximately the positional age of these 2 formations, we can see that they plot within a quite narrow epsilon window. And again, we cannot really distinguish the Deutschland from the Ruihochte formation. And this is also valid for hafnium isotope values here from Detrital. These are hafnium isotopic compositions of detrital zircons, from in yellow the Ruihochte formation and in blue the Deutschland formation, and we can't really distinguish the background, sedimentological background, or the provenance of these 2 formations through hafnium isotopes. What is very interesting is this smaller graph down here, also based on data from Se et al. And Schröder et al. So these are detrital, or the distribution of detrital zircon H's in the Ruihochte in yellow, and the Deutschland formation here for the Se data in blue, and for the Schröder data in reddish color. And we can see that there are very similar patterns with a major peak at around 2.5 billion years. And when we directly look at the youngest detrital zircons between the Ruihochte and the Deutschland formation, they're also extremely similar at 2,353 million years for the Ruihochte and 2,342 million years for the Deutschland formation. I here want to explicitly say that our geochemical data do not provide evidence or proof that the Deutschland and Ruihochte formations are one and the same, and thus were deposited contemporaneously. This is not how our geochemical data work. Our data and those of Detrital show that the provenances of these two formations cannot be distinguished geochemically. That's a very fine difference, but extremely important. Now, one could wonder if these two formations were deposited at significantly different times, would not also the provenance have changed significantly, or at least a little bit? But this really is speculation, and as such extremely risky to do from these geochemical data. So in what is maybe more important and also more interesting from our study by Hafstein et al., which by the way is now accepted for publication in Precambrian research, and I hope that these data will be available online within the coming weeks, is the sedimentological work mainly carried out by Nick Beukes and Stefan Schröder. So Stefan mainly looked at the sedimentology of the drill cores taken from this Aguran project, whereas Nick also observed and described sedimentological successions through the Time Ball Hill into the Ruy-Hochte Deutschland formations throughout many outcrops and drill cores throughout the entire Transvaal Basin here. So there's 11 different profiles, outcrop profiles, and drill cores that Nick looked at and tried to find whether he can correlate these different profiles or whether a correlation is not possible at all. And here are the results of his survey. So you can see the numbering again of the different outcrop or drill core locations. Number 3 here is the Deutschland area. So this is the Deutschland formation. All the other areas are the Ruy-Hochte formation areas. And what we can see here directly is that Nick was convinced that all these sections can be correlated, and his arguments mainly were that at the lowermost part of these formations, you always find a conglomerate, or you often find a conglomerate which is overlined by a diamictite. So you find this in the Deutschland area, but also in other areas here of the Ruy-Hochte formation. You find in the Deutschland area an unconformity in the center of the formation called the Mid-Deutschland or Middle Deutschland unconformity. And Nick could correlate this unconformity also to areas where the formation that is underlying the Time Ball Hill formation, the Ruy-Hochte formation, will also show this unconformity. Sorry for the confusion. And directly overlying this unconformity, he also could correlate a conglomerate, which he calls the Langbacken conglomerate, through many of the Ruy-Hochte and Deutschland formation sections. So through discussions with Nick, it became clear he was more than 100% convinced that one can correlate these two formations and that they were deposited contemporaneously. I want to show you a nice hand drawing from Nick that he made through our discussions about this problem. And he said, yeah, I got so many informations in my notebooks. Okay, I'll make a hand drawing. And it cost him like 1 or 2 evenings to just put together all the information that he had collected in his field notes. And that probably encompasses something like 20 years of field work. And he just took a millimeter paper and drew these very crude but very nice sections through all his outcrop sections he observed, and the drill cores and the correlations that he could find. So this is something I really miss. with Nick this kind of field enthusiasm that he was able to convey to other people. I would like to mention this abstract at the upcoming Goldschmidt meeting in Lyon. Ulyss Hafstein will present data about these drill cores that I haven't shown here, mainly molybdenum isotopes, sulfur isotopes, but also carbon isotopes and more geochemical data. And he'll have his talk on Monday, 10th of July in the evening in session room R11. Should you be interested in this research, please come and have a look at his certainly very interesting talk. Andre Becker allowed me to quickly advertise this position that I've advertised in Earthworks. Should you know somebody who's looking for jobs in isotope geochemistry, or be yourself interested in such a job, go to Earthworks, check out the requirements for the job and what we can do for you, and apply for it. And I would like to finish this talk with this night field picture of Nick and me taken in 2018. And I thank you very much for your attention.
Okay, thanks a bunch. Great. We're going to go ahead and switch over to question and discussion session. You can ask by typing into the messages, into the text, into the chat, or you can raise your hand, which is in the reactions button at the bottom of your screen. And it's the very bottom button after you click reactions. I have one from earlier. K-Sender Sarwan asks, there is a sudden switch in the redox potential of molybdenum in the open ferruginous oceans at 1.7 billion, i.e. the inequality changing. Any specific reason for this, and can increased photooxidation be a reason for this?
Good. Sorry, I didn't get the last. The reason, what could be the reason for it?
Oh, could it be increased photooxidation?
Well, I'm not familiar with that. It's also not really my time frame. I haven't seen these data, so I'll have to answer this on the top of my head. It's hard to say. You see, the threshold value for molybdenum cycling is actually quite low. Molybdenum is also a very sensitive element, and after the GO, we do have small, but we do have elevated oxygen levels throughout the Proterozoic. So I think we find fractionated molybdenum isotope values essentially throughout the Proterozoic into the Neoproterozoic. So I don't see the necessity for a photooxidation to explain these molybdenum isotope values, but I'm really not familiar with the values.
Okay. Cool. At the moment, we don't have any other questions here.
So maybe I can. I have, I guess, one long and one short comment. I sort of don't agree with this correlation between Ruhupte and Deutschland, and it's sort of many reasons for it, and we described it in 2 papers we published in Earth Science Reviews. And but just to highlight few points. First, this ages from Zech. There is a paper coming or will be accepted soon in Precambrian research from Martin Singer from University of Geneva, and they looked over Detrital zircons from paper by Zech, and this 2.3 ages based on 2 zircons were statistically not significant. So that if we are removed when the maximum depositional age of Deutschland would be around 2.45 and different from Röhrucht. So that's something to consider. Another point that the Deutschland formation, as you said, have a major unconformity at the top, to the point that outside of small area, the unit of 1 kilometer in thickness of carbonate platform was completely eroded below the Timble Hill formation, and Röhrucht, which relatively close in the same area, is in conformable contact with Timble Hill. So to me, it makes indicate that we belong to two different depositional basins. And I mean, Nick was 100% sure that Angeluk and Heckport correlate together. And in this paper by Singer, on which he's co-author, now this correlation kind of went away. So sometimes this to be 100% confident might turn out to be incorrect. And the second comment, more simple. So your oxygen constraint based on thermodynamic modeling, to what degree it's applicable to seawater, where most of processes controlled by kinetic, not thermodynamics?
Okay, I have to ask back a question. When you say that the two zircon ages in the publication of See et al. Are statistically insignificant, what do you mean by that? How can zircon ages be statistically insignificant?
Well, if you look at classical papers on Detrital zircon geochronology, it's only 3 and more dates for independent zircons considered to form a peak to Detrital mode. So something like 1 or 2 zircons is not considered statistically significant. And there is now growing literature that laser ablation ICP-MS data can produce artificial ages, both younger and older.
Okay, well, I haven't measured these zircons myself, but they were measured by Axel Gerdes in Frankfurt, and he's a very good analyst, and I would trust him when he puts out the zircon age that he has checked whether this age is good or not. And you know, your statistics that you employ, that I assume is due to interpretation of provenance. But a single zircon, you cannot say a single zircon age is not statistically relevant. If that single zircon gives you an age of 2, 3 something, that's an age, yeah. And that zircon somehow ended up in this formation. But it brings me back to, you see, I don't say our study now provides the holy grail to solve this problem. Actually, I think it opens up the problem. What we need to better constrain atmospheric oxygen level exactly at that time is better geochronological work. It's how should I say that? It's a trying to get sedimentologists in the field together, maybe of these two different schools, and have a look at these sections, and then maybe try to agree whether they can see the similar observations that allow to correlate these different sections or not at all. So I'm not a sedimentologist, but of course you will always find people who say from observations in the field, oh, that's the same, whereas you find others that say, no, that's very different. Yeah. I don't know whether we will be able to solve this problem, Andre.
Well, I mean, for most of community, this problem is relevant only in a way where are multiple rises and falls in oxygen or not, right?
Exactly.
And for this, there is a paper by Simon Bolton in 2022, where within Timble Hill formation itself, he see multiple rises and falls. So regardless of correlation of Deutschland and Timble Hill, there are stratigraphically significant evidence for variations in mass-independent fractionation.
Yes, I completely agree with that. But again, you know, there's other papers like one from Eisen et al. Who didn't find these mass-independent fractionation of sulfur in the Timble Hill. So there's at least some doubt allowed there, although of course it's very difficult when you look at the Bolton data. These mass-independent fractionation of sulfur isotopes are on very small scales in this drill core. So I assume it's very difficult to really sample the Timble Hill and find such fractionations. But again, we have to solve one problem after the other. That's what I want to say. But it's interesting. I have nothing against oscillating oxygen contents during that time. Yeah, I find it fascinating each way.
Yeah, thanks. So there is a bunch of people, so maybe I let other people to go.
All right, great. There was one in the chat that I think is pretty quick, and then we'll get to the hands up. Martin Stenger asks, what lithologies did you target for the study?
We were mainly looking at black shales because in these black shales, when they are euxinic, they can actually best capture the seawater molybdenum isotopic signal. So they will best reflect this molybdenum isotopic cycling. So all our work was mainly done on or was almost exclusively done on black shales.
All right, Greg Vitalik, your hand is up next. Martin said thank you.
Yeah, great talk, Ronnie. I really enjoyed you explaining the systematics of your different isotopic systems, and it occurred to me, I wonder if anyone has ever tried that with the paleosols that are there, like the Borderfall and the Bank Break and the Greek Town. There's several paleosols down there. It would be fascinating to see profiles of these ancient sols and see how they agree with Dick Holland's original ideas. You know, we have ways of getting both oxygen and carbon dioxide out of paleosols now, and your approach might be a really interesting adjunct.
Yeah, thanks for the question. It potentially is very interesting, but I see one problem with paleosols. You know, their lithification process is very risky for isotopes, especially for transition metal isotopes that may become soluble again and then get some odd fractionations that you then of course interpret as original signals. So might be quite risky because of the soil, of the lithification process in paleosols, or later slight burial metamorphism.
Oh, there's plenty of metamorphism in the Borderfall profile. And yeah, you're right. We call that burial glaciation. When the soil sinks below the water table, then things do change. So maybe you're right. Maybe it's hopeless. But nobody's ever done it on a paleosol, these isotope systems, right? Not that I'm aware of anyway. No,
but there's a couple of work that measured chromium isotopes in paleosols. So these are work mainly done by Mike Babetchuk in my group. And we worked on the Flin Flon Paleosol, on the Cooper Lake Paleosol, and on more modern weathering profiles, essentially to investigate whether chromium would be a good redox tool in paleosols, but it turns out it's not, because well, we can't fully prove it, but potentially you can also move chromium-3 around in paleosols, and you can get isotopic fractionation of chromium isotopes without going through redox cycling in paleosols. So we found chromium isotopic signals that you cannot explain with isotopic cycling. And we thought that this most likely is due to kinetic effects involving only chromium-3.
Well, that's too bad. Thanks anyway.
I could speak more to that if you want to follow up later. We have some elemental data of moly and tungsten for some paleosols, and it's indeed complicated. So, and there's good correlations, for instance, of tungsten with potassium in some of the profiles, which, as you know, if you've worked in the paleosol realm, part of that later fluid interaction suggests that the tungsten is probably a product of later fluid flow rather than anything primary, right? That's not universally true, but yeah.
Right. No, we have other ways of getting at it anyway with major elements, but these traces are fascinating. Thanks again.
You're welcome. Thank you.
Okay, Lee Kump, you're next.
Great, thanks. And thanks for the talk. I really appreciate the comprehensive treatment, bringing all those different systems to bear to try to interpret these rocks. I just wanted to remind us all about how little oxygen we're talking about in an atmosphere at that transition point, 10 to the -5 of the present atmospheric level. That's a part per million of oxygen, and the residence time of oxygen, even with respect to long-term processes of burial and oxidation, in that case is a decade. And so 10 to the -5 is not, and various modeling studies have shown, is it's really not a stably regulated oxygen level. And so I think that in a transition from an anoxic to a substantially oxygenated atmosphere, we might expect quite a bit of fluctuation at all scales when we're talking about a residence time that's varying from minutes to thousands of years over geological timescales. So even in the scale of a single length of few tens of centimeters of core, you might expect some fluctuation there if the system that you're sampling is sensitive on those types of timescales. And so I think the other part here, and Andre was sort of touching on this with respect to kinetics versus thermodynamics, but it's also the environment that the depositional environment, the aqueous environment, and relating that to atmospheric O2, because we know, even in a strongly oxygenated atmospheric situation in the Phanerozoic of times with whole basins going anoxic, and so there's that that separation from the atmosphere through the water column to sediments in different depositional settings that makes it really hard to link that back to atmospheric O2. So I agree with you all for those various comments that expecting some fluctuation, evidence of fluctuation of O2 in a transition from a anoxic to substantially oxygenated atmosphere is perfectly reasonable.
Yeah, I actually do agree with that comment. Thank you, Lee. And also, we shouldn't forget, we observe samples in a drill core at the usually 100,000 to million, several million years intervals. And we also shouldn't forget, we usually, at that time, we look at Earth's surface as being static. So there's oxygen buildup through biogenic production in the oceans, and then it goes into the atmosphere, and the atmosphere becomes oxygenated. So it's like we almost treat it as a one-way process. What we forget, of course, is the reducing gases that are released to the atmosphere at the same time, and that might fluctuate as well through volcanic activity, through changing tectonic activity. So I'm pretty sure that there is no just one-way oxygenation of the atmosphere and that was it. There must have been an extended time of maybe fluctuations, very, very low oxygen contents. Yeah, absolutely.
Okay. Xingjun, you were ready to go next, so go ahead.
Oh, thanks, really. That's a fabulous talk. My question is kind of, Andrew mentioned Proton's work on this, and I recall kind of not vivid memory that they do measure TOC in the Draco, and remember there's a little trick, like a little spike in the TOC record in their stratigraphy. So I wonder, in your Draco, did you measure the TOC and carbon isotope?
In our drill course, you mean?
Yeah.
Yes, we did, and we do see a significant change, which I would rather not like to elaborate here because this is the work of Julius Hafsin, my PhD, and this is exactly the work he's going to present at the Goldschmidt. So I don't want to take the big message away from him. I can refer to his abstract and talk again if you want to know about these values, and you're at the Goldschmidt in Lyon or online, listen into that talk and you will get your answer.
Yeah, thanks. Unfortunately, I can't be there physically due to visa constraint, but I will watch it online. Just one kind of quick kind of follow-up comments on this. One thing I noticed pretty weird, not weird, but kind of distinguished about a carbon isotope is that there's no carbonate carbon isotope fractionation higher than 5 per ml before the GOE. I don't know how extensive the dating to this work is, but I think that's a peculiar aspect of the carbon isotope system about this transaction.
I am probably not the best person to answer this question because you see the let's say traditional isotope systems, carbon isotopes, sulfur, well, I do use sulfur isotopes, but carbon isotopes, oxygen isotopes are not really my major research theme. So amongst the group of people here, there's certainly people much better in answering this question, but I'd rather not go in there. I don't know.
Thanks for the fabulous one.
Okay, Kent Condi is ready next.
Ronnie, enjoyed your talk a lot. I have a very interesting question. In the past few years, we've been able to date the thermal magmatic low after the end of the Archean, and it appears like it's centered just about where you're seeing the GOE centered, about 2.3 billion years. Do you think that's a coincidence, or is there some cause and effect here?
Ooh, very good question. So you found the thermomagnetic low below the Kapwal craton at around 2.3 billion years.
Yes. Well, it's 150 million years wide. I mean, it's not a point in time.
Yes. It's difficult to say, really.
Surely that's not a coincidence. Even we don't understand it. It seems to me it cannot be a coincidence that
I'm wondering
level
whether
is building up at the same time.
Yeah, I'm wondering whether this has to do with, the formation of these basins at that time, or whether this is like a build up to the Bushveld complex intrusion, yeah, which is at 2.05 billion years and brings up a huge mass of magma. So I can't imagine that this magma just formed very instantly and then shot up to form this complex, but there must have been like an onset or onsetting process leading to that. And I'm wondering whether your observation may be related to the Bushveld complex rather than to what we see in the oxygenation of the atmosphere.
Well, I think most data suggests the Bushveld was a point in time at about 2 GA, whether it's impact related or whether it's mantle plume related. It's a short period of time, and it's some 200 million years after the thermal magmatic low. Well, it's something to think about in the future anyway.
I will, thanks.
Thanks.
Kent, I think Ronny didn't totally get your comment, but you referring to magmatic lull or magmatic low globally around 2.3 to maybe 2.2 billion years. Is it correct?
Yes.
Okay. But I mean, you're the specialist in these processes. So how would you relate oxygenation of the atmosphere to thermomagnetic signatures?
I have no explanation for this, and that's the reason I asked you. It just seemed to me that it's not a coincidence. There must be
something to think about and keep in mind.
Yes, it is.
Okay, we have Paul ready to go. Paul, you are you're muted.
Yeah, so an explanation for the minimum in detrital zircon frequency could be attributed to a reduced or a lowered flux of reduced gases, which would allow buildup of oxygen. The question is whether that minimum in the detrital zircons is actually real or an artifact of sampling, because there is the Arrowsmith orogeny in the northwestern part of the Canadian Shield and under the cover, which is as large as the Canadian Cordillera and formed between 2.5 and 2.3. And it's just very poorly sampled by any modern river. I don't know whether you have any samples from the Mackenzie River, but it would be the nearest large river. And of course, there's almost nothing draining from that area, and it's been probably close to sea level for 1 billion years or more.
Yeah, that's one of the big problems. I still think that there's a lot to do geochronologically. And I think that is one of the major targets that we should opt at to better constrain the ages of all these formations. Because if these formations are not really well constrained, it's really difficult to concisely interpret geochemical or isotope geochemical data. And with that, the onset or the mode of oxygen evolution.
Yeah, I agree wholeheartedly with that. I think that Transvaal really needs serious geochronological work. There are a number of reported ashes which have, very poorly resolved ages that could be greatly improved with chemical abrasion techniques, and the same applies to those detrital zircons. With a plus or minus 18, it's hard to take such ages seriously. And so those young zircon grains need to be pulled and abraded and dated accurately and precisely.
Yes. Fortunately, I don't have a geochronology lab, so I can't do that work myself.
Well, it's a great tragedy that there's no, Tim's Geochron lab in Africa.
Okay.
Okay.
Well, in the end, that there's enough collaborators, and especially in South Africa, I mean, they do have excellent institutes. They do have excellent field geologists. So if the people like myself take the effort and try to get funding to do better geochronology, I'm pretty sure we can do that. And this is certainly one of the targets that I'll have in the coming years.
Yeah, but it's still coreshed geology.
Say again?
It's still coreshed geology for most of the Transvaal Basin, with the exception of Griqualand West. So, you know, you're dealing with 2 centimeter wide outcrops.
Yes. That is something that Nick always said and laughed about. You know, he said, yeah, you geochemists, you interpret global changes on something that's that big, a drill core.
Well, the problem with the Transvaal is it's mostly nearly flat lying. You know, if it was folded like the Huronian, you'd have complete sections everywhere.
Yeah. You have to take what you can get.
Yeah, no, that's right. And we're you know, lucky to have it and have it where it is, because it's an absolutely one of the most important successions in the entire stratigraphic column. But the other thing where work really needs to be done is reconciling the records of this time in Kopval Craton with those in northern Baltica, you know, in Karelia, because there are some serious issues about when the GOE occurred. I mean, in Karelia, it looks like it's more like, you know, 2480 rather than 2340.
Yes, yes. But also with Australia, actually, when you look back at the, you know, some work that has been done in correlations between Australia and South Africa, there's also several observations that do not really match up the GOE precisely, especially the sulfur isotopes in these two, in these different basins. So there's still a lot of work to be done. Yeah, we're not done yet.
Well, I mean, reworking of the MIF is a serious problem. So I think we need to, you know, pay more attention to the very large MIF anomalies, you know, the ones of a few per mil, and not take so seriously the ones that are a few tenths of a per mil. Now, the problem with Western Australia is that it doesn't seem to have great, you know, radiometric geochronology potential there, unlike Karelia and Kopval. So the dating, you know, better, you know, chronology is absolutely critical. I mean, you know, we were in the same situation in the Neoproterozoic before we had a chronology. And once we had a chronology, it's not quite complete, but it's, you know, it's getting close. Then we could have something we could grab onto.
Yes. I think there's a lot of people who are interested in that and potentially will try to work on that. Thank you, Paul.
Well, if there was as much work on the geochronology as there is on the geochemistry, I think we'd be farther ahead.
Maybe this is sort of a broader comment question here, but it made me think of it, is whether we should be really thinking of the GOE as this one single event and what defines that, or more of like an episode, a sort of protracted episode. And maybe Andre can speak more to this as well. But I mean, should we define it as this loss of SMIF or define it as a larger event? And
that's the question. It remains to be determined. And
yeah,
it's not a matter of definition, it's a matter of observation.
Yeah, fair. It seems interesting to me that, like, well, it's maybe sort of trivial, but when it can come down to like something like defining a boundary between the Archean and the Proterozoic, this could be, you know, maybe the most obvious important thing to use, right? And is this loss of mass independent fractionation a thing that at some point we should be considering as that boundary?
Well, I agree with Ronnie. Bistability in oxygen at low oxygen levels is quite possible from from as far as I understand the the atmospheric and geochemical dynamics. So that can't be ruled out that there's oscillation. I think that might well be the expectation. But as geologists, our job is to determine the record as accurately and precisely as we can.
Yes, as it stands right now, we do see fluctuations in the two formations I was talking about. Andre mentioned that there are fluctuations found in the overlying Time Ball Hill. We got the oxygen overshoot in the Lomagundi event, but we've also heard that there's criticism about that because it's only actually recorded in surface environments. But certainly at the moment, what we know about the evolution of oxygen and the increase of oxygen or the oxygenation as such of the atmosphere, it is not one single shot in Earth's history. So for the moment, with the knowledge that we have at this time, I would rather call it an event, an episode, because, even if it's just 50 million years, 50 million years is a lot of time.
Yeah, and just
two other points. The question of TOC came up, and I was staggered by the volume, by the mass of the warm, deep crustal biosphere. I mean, I don't know that it's very active, but there's a lot of carbon down there, and so the question about TOC and old rocks is, what's the age of the carbon?
Are you talking about the carbon deposits in the Shunga event?
Well, no, this was the question about the small fractionation between carbonate and organic carbon in the pre-GOE.
Mm-hmm.
Someone mentioned that there was only 5 per mil, which would be very surprising. Although, I'm not sure how much we know about. Well, we're now told that that oxygenic photosynthesis is actually ancestral, and so it's surprising that it would only be 5 per mil. But of course, that all depends on the assumption that the two carbons were coming from the same reservoir at the same time.
Ava, did you want to comment on this, or?
I had a separate question. It's not related to this.
Okay, well, you can also go instead, or unless Ronnie had something to mention on this one.
No, not really. Again, it's not my home turf, so I'd be on very thin ice to try to interpret any carbon isotopes and deposition of organic material at that time.
Okay, go ahead, Ava, then.
Yeah, first, thanks for your talk. I was curious about these EH changes that you showed. So, because usually I think of EH as being buffered by something. And so are you imagining what are you imagining in terms of redox buffers that are evolving across that time interval? So, I guess it would be iron probably, or sulfur, or I don't know. What do you think?
It's very difficult to say, really. First of all, I gotta say, when you look at Courbet diagrams, EH-pH diagrams, they're always defined or depending on temperature, concentration, pressure. So when we look back, maybe I can quickly go back to this graph. Here you can see here at what conditions we drew these graphs, and these are maybe not exactly the oceanic conditions that we had at that time. It's really difficult to tell. Yes, these values can be buffered, but it's also very difficult to say because we still don't know what exactly was the pH of the ocean at that time. Was it actually alkaline or even a little bit acidic? So I have no imagination what really could buffer all these processes or these elements. It's very difficult to say. It would be a lot of speculation.
Yeah, makes sense. Yeah, thanks.
Okay.
So Martin Singer was raising his hand, maybe. Or
Yeah, he just put it into the.
I can ask it here if you want. So thank you very much for your talk. Before anything, I wanted to add that now I'm finishing my PhD student. Sorry, I'm finishing my PhD under the supervision of Urs Schaltiger in Geneva. And well, first we have dated some of these rocks in both the Griqualand and the Eastern Transvaal, but most importantly, we have also measured the sulfur isotope record in pyrites preserved in these shells of the Kuruman Banded Formation, as well as molybdenum isotopes like bulk rock molybdenum isotopes in the Kuruman Banded Formation from one drill core only that has been dated in 3 years ago in Lanting and collaborators in 2019. And the point is that we have found, or we think so, at least we are interpreting this way, that we are seeing fluctuations in oxygen even before this discussion you were addressing between the Roy-Hoogte and the Detrital formation and the loss of the mass independently fractionated sulfur in between the two units. So I personally think, and I agree with Gamsley and all these works, that we have actually a fluctuation, a series of multiple oscillations in oxygen. And maybe in the case that the Roy-Hoogte and the Detrital formation are indeed not equivalent, it could be completely acceptable that they just record different things.
I have to ask back. So your observation of oxygen fluctuations in your Kuruman core, and you're talking about that core that you worked on regarding climate changes at that time. Yeah. Milankovitch cycles.
Yeah.
Did you find these fluctuations based on molybdenum isotopes or multiple sulfur isotopes?
So this drill core goes all across the Kuruman and goes into the Gamohan formation at the very top of the Campbell-Grant carbonates. And we see that there is a fluctuation, like a first order trend from molybdenum isotopes from very heavy values at around 1.1, 1.2 positive towards very negative values at around minus 1.0 all along across the core. And then we also sampled those levels and horizons that contain pyrite, and we measured them with the SIMS at Lausanne. And we also found that there's fluctuations, there's different signals between like large MIF values, let's say 4 to 5 per mil to 0. But it occurs not as an unidirectional change, but as back and forth changes. And the topmost sample we managed to measure these pyrite crystals contained like practically MDF. So we see the two changes, one that is like a larger scale and the other one that is maybe rapidly shifting.
Okay, I have several comments on this. I mean, I don't know your data, but first of all, of course, you can get fluctuations in molybdenum isotopic compositions before the GOE. This is, long known. We got fractionated molybdenum isotope values in the 2.95 billion-year-old Pongola basin. These are data published by Noah Planowski and Franz Ossa. So way before the GOE, way before the disappearance of MIF sulfur, we already see fluctuations of molybdenum isotopes, so I'm not surprised by that. And as Paul said, you know, with multiple sulfur isotopes, we also got to be careful with redeposition of earlier material, which will homogenize signals. And we also got to be careful with interpreting single point large or capital delta 33S signals, because from the atmosphere at any given time, we're depositing negative and positive values, and they might get remixed again. So just because in one or two samples in a succession you see mass-dependent fractionation or the absence of mass-independent fractionation of sulfur isotopes, I wouldn't directly jump on the bandwagon and say that has to do with oxygen in the atmosphere.
Yeah, that's completely correct. But in this case, the two proxies are indicating separate things. That we have oxygenated shallower, in the Klein and outer shell, we have oxygenated conditions in the seawater, but anoxic conditions. And then it's true that the MDF does not necessarily mean that it was oxic, because it could have been mixed, the signal. But this crustal memory effect, it's also being contested in several papers, even some papers, I think it was Torres and collaborators in 2018, for instance, that they did not measure mass independently fractionation of sulfur in rivers running, for instance, in modern environments. And then the paper from Uveges that was published this year in 2023, that also challenges how effective, if at all, was this so-called memory effect.
Can't really say anything on that because it's a model. I didn't look into the particulars of that model, but yes, I'll think you'll find as many arguments for it as you'll find against it.
Yeah, they find MIF in diamonds that come out of Cretaceous kimberlites.
Okay.
So one thing that maybe since Martin here, I can kind of explain what I didn't mean that the data analytically incorrect, but it's just a nature of laser ablation ICP-MS that error bar is large enough that it's hard to discriminate concordant and discordant ages. And for more important ages like this, we should repeat them with teams. And maybe since Martin and audience, maybe Zach could provide him with this zircons and he can try to repeat it. And that would be a good test eventually for correlations or not.
Yeah, so the problem we found with that, with the data set from Z for these particular samples is that they mostly are based on two concordant analyses that are much younger than the next cluster. However, this could be either that it's an undersampling bias because the N of the amount of crystals that were measured in the sample are not that high. So maybe it is correct that that's the correct age, or it could also be that in such old sequences, it's very well known that you have lead loss effects on all these crystals. In fact, we've actually measured for zircons from the Makaniani formation, but we saw that there was a 200 million year gap between the youngest concordant cluster of analysis and this next one, the following cluster. And what we concluded after dating them with the laser and then with the teams, we actually could not date them with the teams because these zircons dissolve during the chemical abrasion step very, very fast, which usually happens when you have zircons that are highly metamixed. So this is also an open possibility that we should try to, if possible, it's not always the case, but it's better to try to at least chemically abrade these zircons before, especially for all sequences like the Transvaal supergroup, to chemically abrade them in order to avoid measuring or misinterpreting younger clusters measured in samples. So I'm not saying that the Deutschland or the formation are necessarily the case, but this is always a problem that we should be looking for, the geochronologists. So this is the reason why maybe it's not that reliable, these two analyses published in Z for the Deutschland formation.
I'm a little bit surprised, I have to say, how easily people dismiss ages, yeah, concordant ages. I'm a little bit sorry to say, but I agree that, of course, chemical abrasion should be done if you really want to do good geochronology on zircons in these formations. But just to discuss away an age so easily before it's actually been proven that there might be some lead loss effects on the surface that alter the age of the zircon, I'm yet very reluctant to do that.
Well, it's been demonstrated from comparison with in situ ages and CA TIMS that there can be tens of millions of years error because of early lead loss. It's a very serious problem.
I'm very well aware of that, Paul, but you cannot just dismiss any, uranium lead zircon age that has not been measured on a braided zircon by TIMS just based on these observations. Probably you will find as many studies that show that these ages very well agree because these zircons didn't undergo lead loss. Yeah,
the point isn't to dismiss the age. The point is to encourage proper dating.
Yeah. Oh, absolutely. I'm fully with you there.
Well,
when we look at the ages that Martin was talking about of the Kuruman that they measured in the lab in Geneva, these ages have uncertainties of plus minus 1 million years at 2.4 something billion years. That's the kind of ages that I'd like to see in all these formations, of course.
Okay, Don Davis's hand is up.
Yeah, this seems to be a persistent topic of argument here. I wasn't going to say anything about it, but since it's continuing, the problem with using the youngest age from something like a detrital population measured by LAICPMS is that it's almost certainly younger than the actual age. Just imagine that you had only one source of the sediment, so everything was one age, but you're measuring a probability distribution with plus or minus maybe 20 or 30 million years around that, but you're looking for the youngest element of the age, and you don't know they're all the same age. You have to assume they're all different. So what you're going to do is pick a sample that's on the younger end of the tail. So almost certainly, if you take the youngest detrital zircon age, it will be younger than its average will be younger than its actual age. So of course, this doesn't matter very much with ID-TIMS because your errors are plus or minus 1 million years. But if you've got plus or minus 20 or 30 million years, then it can be a substantial underestimation. So there's been many papers written on how you should do this, but in my opinion, the only reliable thing you can do is take the 95% confidence error in the older direction and say there's a 95% confidence that the age is no younger than this. So if you have, for example, 2,500 plus or minus 30 million years, and you have to say there's a 95 at 2 sigma, 95%, you have to say there's a 95% confidence that it can't be any younger than 2530.
Yes.
2,500 plus or minus 30 doesn't mean anything. There's no error bar associated with this. It's just a confidence interval. So that's assuming you didn't have laboratory contamination or lead loss or something else. If you assume that your measurement is taken from a random distribution and there's nothing biasing it, then this is the best way to interpret your youngest detrital zircon, the upper age limit on deposition, basically. So that's my 2 cents.
Yeah, it's a good way to start.
Yeah, maybe we should invite Urs or some other geochronologist or Don to give a few examples like of complications with laser ablation and CPMS. I think it would be useful for community.
Yeah, I have to skip. So Andre, if you want to keep the conversation going, feel free. Thanks, everybody. I'll see you all next week.
Thanks, Alex.
Thank you.
And Ronnie, great work.
Okay.
Thanks.
Well, we gave plenty of questions to Ronny. Any last minute questions? Or... Okay, so
I summarize, we need better geochronology. Most important.
Yeah. Okay. Thanks, Ronny.
Yeah, I mean, just think of the impact of the Gumsley age on the outlook.
Yes.
Okay, great. Thanks, everyone. And we reconvene next week with another speaker from University of Tuebingen, Andreas Kapper. And thanks again, everyone. Bye.
Thanks.